Thank you for the introduction. Yes, I'll pronounce my own name. My name is Roland van Rijswijk-Deij, so that's why he said Roland. It's kind of hard to pronounce for non-Dutch speakers. I'm going to talk to you about the use of elliptic curve cryptography in DNSSEC, so a completely different topic. I work for SURFnet, that's the National Research in Education Network in the Netherlands, and I'm also a part-time researcher, so I have a night job at the University of Twente, which is one of the universities on our network. So, very brief introduction. Unless you've been sort of hiding in a closet somewhere, you will have seen that DNSSEC has been going on for a while now, and deployment has sort of taken off. Most of the big TLD operators have deployed it, and lots of second-level domains are starting to deploy it as well. In some TLDs more than in others, and I'm kind of proud that in the Netherlands, almost 50% of domain names are now signed with DNSSEC. But it still has operational issues. There are two sort of operational problems that are to do with response sizes, and one is fragmentation and the other is amplification, and I'll give you a little bit more detail about those in the next couple of slides. And the other one is that the management of a DNSSEC signed zone is kind of complex, and there's complex key management involved. I'm not going to go into details, but there will be some pointers at the end towards some more information about that. Now, fragmentation. Fragmentation is an issue with many protocols on the internet, especially protocols that mostly use UDP, like DNSSEC. And again, just like with TCP fast open, there are nasty middle boxes that stop your fragmented packets from reaching their destination. We did a study a couple of years ago where we found that up to 10% of DNS resolvers may not be able to receive fragmented responses, and that results in a degraded user experience because people have to wait longer for the names to get resolved. And there are already some solutions out there. You can configure your authoritative name server a little bit differently if you're a DNS zone operator, because of course you're affected by the bad behavior of the resolvers that can't receive the fragmented responses. The fallback behavior in resolver software was improved over the years, and the RFC that deals with how you transmit large DNS responses was changed in the update 6891, where they said that if you are aware that there are firewalls on the path or other middle boxes that muddle with your packets, then you should not be asking for big DNS responses. So what happens if you turn minimal responses on? Well, that pays off. This is a graph for one of our authoritative name servers. We had lots of problems when we first deployed DNSSEC with people being unable to resolve names in our zone. And that was mostly due to the large responses, and we changed to minimal responses, and as you can see, the average response size from our authoritative name servers dropped by about 66%. But even if we turn minimal responses on, we still see fragmentation, and about 0.1% of packets that go over IPv4, the red line in the bottom graph, still get fragmented because they don't fit in a single packet. The other problem with DNSSEC, of course, and that's been in the news a little bit lately with Akamai saying that this is now getting abused a lot for DDoS attacks, is that DNSSEC is a potent amplifier. We did a study in 2014 because there were lots of claims out there that DNSSEC had this huge problem that you could use it for amplification attacks, but nobody had actually measured it at scale. And what we did is we looked at all DNSSEC signed domains in .com, .net, and .org, and a couple of other TLDs, and measured what kind of amplification you could achieve with these domains. And you can see the result in this graph. On the left-hand side are our sort of control group of domains which are not DNSSEC signed, and what we did is we sent, in this case, this is the data for any queries, we sent 2.5 million domain names that were not signed in any query, and then the average amplification factor that you could achieve is around about 5. We did the same for 2.5 million DNSSEC signed domains, and the average amplification factor is somewhere around 50, with outliers going up to 180 times. So DNSSEC is a potent amplifier. But is there a reason behind this? Well, we argue, if the button helps me, oh, sorry, one more slide, yeah. So any queries we could suppress, right? Any queries is something that you use for debugging your DNS, and there's actually a draft circulating in the IETF to deprecate the any query in a sensible way such that you only give a very minimal response as an authoritative name server if you receive an any query. But if you do DNSSEC, you have to communicate the keys that you use to sign your zone to other people, otherwise they can't validate your responses. And that is done with a specific record type called DNS key. And unfortunately, if you send all your key material, that's going to be a big response. And what this graph shows you is for those 2.5 million domains for which we did the measurement study, almost 40% of those give you an amplification factor of over 23, and 23 is sort of a magic number because that is the amplification that you could achieve theoretically if you used classic DNS packets of up to 512 bytes. And we deem anything that you reach above that, any amplification above that, as bad. And 40% of DNS key responses that we got back exceeded this limit. And we argue that the root cause for this is RSA. RSA is the only mandatory algorithm in DNSSEC. It is also the one that is most widely deployed. And the problem with RSA is that the keys are large. Say a 1024-bit RSA key already gives you 128-byte signatures, and every DNS response may include several signatures because you have different record types in there or because you have additional information in your packet that also needs a signature. And then if you go to 2048-bit RSA, the signature size doubles because the key size doubles, and you may have 256-byte signatures in your packet, which means that if you have 2 signatures, you've already filled a classic DNS packet with data. Another issue with RSA is that we have to keep growing these keys. I think there's going to be a talk about this in the DNS session tomorrow. The root zone is going to migrate its zone signing key size to 2048-bit RSA, and the key signing key is already at that, but the majority of signatures in the DNS zone will be done with the zone signing key. So if the root moves to 2048-bit zone signing keys, that means all the signatures that you get back on the TLD referrals that you get will also have larger signatures in there. So is there no solution to this problem? Well, we think there is, because there are good alternatives to RSA, and the most obvious one is to use elliptic curve cryptography. Now, ECC has very nice properties because it gives you much smaller keys and much more cryptographic strength. As the slide shows you, a 256-bit ECC group is equivalent in strength to 3072-bit RSA, but the signatures are 4 times smaller than 2048-bit RSA signatures. And actually, it turns out that ECDSA, which is one of the elliptic curve signature algorithms, was already standardized for use in DNSSEC in 2012. With 2 curves, one with 256 bits and one with 384 bits. Unfortunately, it's still used very little in practice. 98.2% of signed.com domains still use RSA. But there is a lot of buzz around it. If you go to ICANN meetings or if you go to the IETF, then you will see people talking about using elliptic curve cryptography in DNSSEC. And actually, there is one large operator that has already deployed this at scale, and that's Cloudflare. And they are responsible for the 1.8% of signed domains in .com that use ECDSA. And apart from ECDSA, there are additional algorithms that are currently getting standardized for use in DNSSEC. They're called EDDSA, and they have some even more favorable properties in terms of mainly key size when you transmit it across the wire. So what we wanted to do was to measure the impact of if we switch DNSSEC from using RSA to using ECC overnight, what would happen? What would the impact be on operations? So we revisited all those domains in ComNet and org that are signed that we looked at in the amplification study, and we tried to estimate what the effect of switching to ECC would be. And actually, that's very favorable. If we go back to the DNS key response sizes, then if you look at this figure from right to left, then the current situation is the dark line on the right-hand side of the figure that shows you that round about the top 10% of DNS key responses that we get for ComNet and org zones don't fit in the minimal MTU size for IPv6, and round about 1% don't fit in the minimal MTU, or in the usual MTU, so 1500 bytes for Ethernet, which is what you see for IPv4 mostly. But then if you would switch to ECDSA, then even if you use ECDSA with a conservative scheme, so you don't change the DNSSEC mechanics, you just change what algorithm you use to sign the zone, then your responses will become a lot smaller, and all of them will be below 1024 bytes, so they'll easily fit even into the minimal IPv6 MTU. And you can do even better, because the keys in the, ECC are a lot stronger. You could choose to sign your zone with a single key rather than using the current scheme, which has a dual setup where you have a key signing key that only signs your key set, and you have a zone signing key that signs the names in your zone. You could move to a single key, in which case you could fit your DNS key response in a classic 512-byte DNS packet. So the impact on amplification is, of course, that amplification will be way less. The red bar at the bottom shows you the span of amplification that we saw with the original measurement that we did, and if we switch to ECDSA, obviously amplification becomes less, and as I said, we could argue that any should be banned anyway. If you look at the amplification that you could achieve with DNS key responses, as I said, any we can block DNS key we need to do DNSSEC, then the takeaway is that if you switch to ECDSA or EDDSA, then DNS key amplification is no longer a big issue, because you cannot achieve more amplification with DNS key responses for this algorithm than you could with a classic 512-byte DNS packet. And I think that's good news. And maybe if we go to ECDSA or EDDSA-based signatures, we could go back to classic 512-byte DNS, because we also looked at the bread and butter of DNS, so the A and quad A responses. And what you can see is that all of these would fit in a classic 512-byte packet, which if you were to use RSA together with DNSSEC would not be the case. And there is, of course, always one little problem. Unfortunately, the standardized ECC schemes in DNSSEC can be a lot slower when you validate the signatures. And this is actually something that they mention in the RFCs. They say there that validation of ECC signatures may be up to, I think they quote something like 5 times slower. And it's actually a lot worse than that. The majority of RSA signatures that you encounter today in DNSSEC are 1024-bit RSA signatures. So what we did in this table is compare the validation time for 1024-bit RSA signatures to the smallest ECC group that was standardized, which is P256. And if you use current software, so current OpenSSL to do the validation, validation of a single elliptic curve signature can be up to 26 times slower than a 1024-bit RSA signature. And that might be a problem, because you might be pushing the effort towards the edges of the network. So right now, validating DNSSEC signatures is not an impediment for DNS resolvers. Validating resolvers can run on just the same kind of hardware that you were running your DNS resolver on before. But what would happen if you switch all of DNSSEC over to elliptic curve cryptography? Can we still do that? Or is the CPU penalty on resolvers going to be so extensive that we can no longer do that and we need to upgrade our resolvers? And we wanted to find out before we recommend people deploy this at scale on the internet. So what we did was we studied resolver behavior, and we looked if we could predict how many signatures we have to validate and what kind of CPU we would need to do that validation. What you see in the picture here is the chain from the DNS resolver towards authoritative name servers and the number of signatures it needs to validate. So clients we took completely out of the picture because the cache takes care of that. What we want to know is what kind of responses does a DNS resolver get back. And if you look at the picture from top to bottom, you see that the DNS resolver will send a query to authoritative name servers, not all authoritative name servers will respond, so we look at that factor first. That's number one. The second thing we look at is which fraction of responses contain signatures, because not all domains are DNSSEC signed, so we need to figure out how many signatures we get in anyway. Then we measure the average number of signatures per signed response, and finally we look at which signatures the resolver actually needs to validate. Because if it's validated the signature before, or if there is no chain of trust, the resolver does not have to validate the signatures, so it doesn't expend CPU cycles doing that. What we did was we measured this on production traffic. So SURFnet is a medium-sized network operator. We have about 1.2 million end users on our network, and we operate resolvers for these people. And what we did was we took the traffic that is flowing towards one of our production resolvers, and we sent that traffic to an instrumented DNS resolver. And what we do is we measure the number of outgoing queries. We instrument the resolver to measure how many signatures it validates, and from that we try to predict what happens if we switch that over to elliptic curve cryptography. And we observed all of this behavior for the picture that we had with the digits 1, 2, 3, so all the various variables that are in there. And the takeaway from this picture is that it's mostly linear behavior. So to take an example, diagram number 1 on the top and left side shows you that the number of responses that come back for every query that the resolver sends towards authoritative name servers on the internet. And it turns out that about 90% of queries that the resolver sends out to authoritative name servers get a response. And because this is mostly linear, we can use this to predict future signature validations. So we wanted to evaluate 2 scenarios. And the first scenario is for current DNSSEC deployment. If we switch that to ECC overnight, what would happen? Well, it turns out that on a moderately busy resolver, and our busiest resolver processes around 20,000 queries per second, we require about 150 signature validations per second, and that is easily doable on modern hardware. The CPU won't sweat if you do that. However, what if DNSSEC becomes a huge success overnight, and 100% of domains on the internet enable DNSSEC? What would happen to resolvers in that case? And we wanted to study a worst case scenario. And the worst case scenario is where popular domains, and we measured what popular domains are, so let's say google.com, deploy DNSSEC first. Right, because that means that the majority of responses that we get, we will need to validate signatures on. Now, if you look at what is popular, this is a plot of the popularity of a query name, so how many queries we see for it versus ranking in popularity. And then what you see is that this is what is called a ZIP or a long tail distribution, and that means that the most popular domains are responsible for the vast majority of queries. And this is a log-log scale, so it becomes a line, but if you plot this, it looks like a curve that has a very steep drop-off towards the end. And we looked at 2 kinds of DNS resolver software to see if we could predict what the impact would be if people switched to ECC. We looked at 2 kinds of software. We looked at Unbound from Nelnet Labs, which is the software that we use. It's a dedicated open source resolver-only package. If you've never heard of it and you've never looked at it, please have a look at it. It's really good software. We really like it. And what you see in this graph is a prediction what would happen for various amounts of DNSSEC deployment. The plane that you see is the threshold of how many ECDSA P384 signatures, so those are the signatures that require the most CPU time, we can validate on a single core. And on a single core, we can validate about 1,200 signatures per second. But then if you look at how many signatures we would need to validate, then you see that if DNSSEC deployment grew to 100%, based on the real-world measurement data that we have, we would still be able to validate all those signatures on a single CPU core. So that means it's not an issue. We can deploy ECC overnight and it wouldn't kill our resolver, which is a great result. But then we also looked at Bind, which is still, I think, the most used software for DNS on the planet. I think their market share is still around about 50%, if I remember a presentation by Jeff Houston correctly. And what you see there, that there's a slight problem. If DNSSEC deployment were to grow from its current state, where it's at now, to around about 10% deployment, and we're currently at about 3%, Bind would struggle to validate the signatures on a single CPU core. But that's not the whole story, because it would struggle to validate the signatures for the most CPU-intensive algorithm that we have, which is P384. And actually, in practice, people will most likely use the other one, P256, because it is more than strong enough. And actually, if you look at the large operator that currently deploys ECDSA, Cloudflare, they use P256. There are other lines in the graph. You can have a look at them in the slide deck. The slide deck will be online. Show you what's the case for P256, and even Bind won't struggle with P256. So again, the takeaway is we can safely switch to ECC without killing resolvers. So what does that mean? Well, I hope I showed to you that switching to ECC is highly beneficial and tackles some problems that we have in DNSSEC. And both amplification and fragmentation are a result of DNSSEC responses being much larger than classic DNS responses. But if we go to elliptic curve cryptography, that's no longer the case. And it could even bring that good old 1983 512-byte DNS back, because we can fit most of the responses that we would need in a smaller packet. The impact on resolvers is well within reason, and there are actually many improvements being made to elliptic curve implementations. And for instance, Cloudflare, who have deployed DNSSEC on their infrastructure, have contributed an improvement to OpenSSL that speeds it up by about a factor of 4. There are still some open issues, and the biggest of these is resolver support for ECDSA. So not all DNS resolver software currently supports ECDSA. And Jeff Houston and George Michelson from APNIC have done a measurement on this, and right now about 80% of resolvers out there support this, but that still means that 20% don't support it, and that's mostly due to intellectual property fears. Some Linux distributions, such as Red Hat, in older versions do not include elliptic curve crypto at all, because they were afraid that they were going to get sued because of intellectual property on elliptic curves. But fortunately, all modern releases support ECC. So what would it mean for you as operators? Well, what I would say is DNSSEC deployment currently is around about 3% of domains worldwide. So that means 97% of domains are not yet DNSSEC signed. And if you're planning to deploy DNSSEC, then my recommendation would be don't go with RSA, sign with ECDSA P256, or if you're waiting a little bit longer, go with one of the EDDSL algorithms. And if you have an existing deployment, you should start thinking about switching to ECDSA. Unfortunately, that is not trivial, because it requires you to do something that is called an algorithm rollover. I don't have time to go into the details. Look up the RFC. It gave me a headache. But we will be doing this in 2017. So hopefully we'll post a series of blog entries about that that will make life easier for you if you want to do this. If you operate DNS resolvers, so if you're a large network operator, you operate DNS resolvers for your customers, check, and if you do DNSSEC validation, please check if your resolvers support ECDSA. If you don't yet do DNSSEC validation, but you're planning on deploying it, make sure that the software that you pick and the platform that you use support elliptic curve cryptography. This is there for reference. The slides will be up, as I said. These are some papers that give you much more detail about all the issues that I discussed in the talk. I would like to point you to our blog, dnssec.surfnet.nl, which is currently horribly out of date, but which we will be updating when we do our algorithm rollover. So when we switch our infrastructure over to ECDSA, we will be posting entries on our blog about that so that you can learn from our experiences, and hopefully you won't have to learn from our mistakes. That's it. I would like to acknowledge the work of my master student, Caspar Hageman, who did all the measurements. And with that, I open the floor for questions.
Mike Sinatra, ESNet. Nice talk. Thanks for that. I think one other thing you're going to have to look at as a signer is whether your registrar supports ECDSA. Yeah. Not only are there a lot of registrars out there that do things like Common Net, but they still don't support DNSSEC at all. But even a lot of the ones that do don't support the elliptic curve algorithms, unfortunately. Yep. There are 3 or 4 who do. I know Google Domains does, and GoDaddy. Those are just the ones I know that do support it. So you have to be careful with that as well. Yeah,
that's actually an excellent point. We just submitted a paper about that particular issue to a conference, and unfortunately I wasn't able to include those results. But that's an excellent point. Yes, your registrar needs to support the algorithm which you sign with. And for instance, for Cloudflare, we see that this is actually hampering adoption. So from the top of my head, 40% of the domains that were signed with their service don't have a full secure delegation because the registrars don't support ECDSA delegation. So it's an excellent point. If you sign, check for that.
Ryan Rodden, Conversant. What is the failure mode when resolvers don't have a version of OpenSSL or their crypto library that supports ECC validation?
The failure mode in that case is that they don't validate the signature, and you will get a response without the so-called AD bit set. So you will still get a valid response. It won't be treated as bogus, but the signatures won't be validated either. Any other questions? Okay, thank you very much for your time.